All right, let's get going here. Today we're going to do the last chapter before our first exam. Isn't that exciting? In this chapter we're going to do chemical bonding and going to do nomenclature for ionic and molecular compounds. Before we do, just one more reminder. There are people that have not done very many of these. Remember, you do them twice. Leave the default email address just like it is. That will come to a special mailbox. And instead of putting your email address, simply put your name. All right? 5 points. Don't waste it. That's 5 points for all of these or each of these. And that is added to your exam score. Any questions? This offer, of course, becomes invalid just before the first exam.
When is that?
It'll be, let's see, next Wednesday we're going to do a sample exam. So we'll go over that in class, and then the week after that.
Wait, so the sample exam is like a fake test?
Yep.
Is it going to be like for a grade?
Nope, not for a grade. What I do is I post it up on Blackboard. Everybody prints it, work it at home, and then bring it in. We'll go over all the questions. If you have any questions, ask them. All right, we've talked about compounds. We said that there were 2 basic types. We will call them molecular and ionic. They differ in the type of bonding. In an ionic compound, you tend to have an array of ions. These will either be positive or negative, and they just kind of stuck together electrostatically. A molecular compound, you have a set geometry, and you have covalent bonds. So that's electron sharing. Now, we saw covalent bonds when we did Lewis structures. We'll review some of that today. This is just another example of a organic compound. Remember, you can also have double and triple bonds that are formed between adjacent atoms. This is sodium chloride, and it's an array. It's an array of the chloride anion. That anion is negative, and the sodium cation. And once again, they're just stuck together electrostatically. Positives and the negatives attract each other, and they form these continuous arrays. Now, this is a representative. We know that carbon has electrons in 2 levels. The core electrons are the ones close to the nucleus. They don't do much. We don't care about them. And these guys out here are the valence electrons. When we do bonding, we're going to be dealing with valence electrons. We will either add electrons, take electrons away, or share in this valence shell here. Once again, the nomenclature here. When we have a positively charged ion, we will call that a cation. When we have a negatively charged ion, that will be an anion. When you have an ionic compound, you simply have an extended array of the positives and the negatives. This, as you see, is in a very regular way. This is a crystal. If you actually look at a crystal of sodium chloride, you'll see it has beautiful sharp edges. It's cubic. That's because the crystal structure here is also cubic. And this array just goes on and on and on. And that's why you get such nice, clean, sharp edges. Well, when you're dealing with ions, we said that this is a chloride anion, it's a -1 charge, and this is a sodium cation, +1 charge. The first question you should ask is, how do you know that? How do you know that chloride is going to form a -1 and that sodium is going to be a +1? Well, if we go back to our old friend, the periodic table, it's actually very, very simple. Remember, we ignored the fact that there are really 18 across, and we just did the groups 1 through 8, because those represent the simple valence electrons. Well, they also represent nicely the charges for the ions in that group. Anything in the first group here is going to form a cation with a charge of +1. Anything in the second group is going to form a cation with a charge of +2. When we get over here, it gets a little bit iffy because we have semi-metals and we have funny things down here. But right in this area anyway, the metals are going to form cations with a charge of +3. Again, down here, it gets a little spooky again, but this would be +4. So up to group 4, we're going to form cations or molecular compounds. Group 5, 6, and 7, we're going to form anions. So here we're adding an extra electron to the valence shell. Anything in group 7, fluorine, chlorine, bromine, iodine, these guys are going to form a -1 anion. Anything in group 6 is going to form a -2, and anything here in group 5 would form a -3. Any questions? It's actually very, very simple. When you go to put an ionic compound together, the principle of charge balance simply says that you must have the same number of positive charges as you do negative charges. So the two things have to balance out. For a compound formed between magnesium and sulfur, magnesium is group 2, it's a +2 cation. Sulfur is group 6, it's a -2 anion. The +2 -2 cancel, the net charge is 0. Sodium and bromine, group 1, group 7, +1 and -1. Again, we go for a net charge of 0. Sulfur here is -2. That means we're going to need 2 sodiums in order to balance out the charge. Two positives, 2 negatives, again we get 0. And we have magnesium +2, we would need 2 bromine -1s, again to get us to our negative or our 0 charge. Principle of charge balance is very simple. The compound that you make must be neutral. Same number of positives as negatives. All right. When we go to represent an ionic compound, we're going to simply put down the cation and the anion. And we're going to do this in the lowest whole number ratio. So if we were to write magnesium, the compound for magnesium and sulfur, we would simply do MgS. 1 magnesium, 1 sulfur. If you put bigger numbers, Mg2S2, well, that's still neutral, but that's wrong. You always go to the lowest whole number. Sodium bromide, 1 sodium, 1 bromine. Here we have 2 sodiums and 1 sulfur. And again, we use a subscript here to indicate there are 2 sodiums, 1 sulfur in this compound. 1 magnesium, 2 bromines, and it's simply written like that. Any questions? All right. We can write the compounds. We can make sure they're neutral. What are you going to name them? The naming is actually very simple. Well, I guess naming is on the next slide. This is the concept called a formula unit. So let's do that one first. Formula unit, that's, everybody wants to call these a molecule. Legally, it has to be a molecular compound to call it a molecule. Instead, for an ionic compound, the correct thing is to refer to it as a formula unit. And again, it's the lowest whole number ratio of the atoms, just like the formula that we wrote. This is not a molecule of sodium chloride, it is a formula unit of sodium chloride. Remember, that's because these things don't exist as units, individual units. It's long extended arrays in all directions. So that's why they do this. It's a little unwieldy. I'll probably call them molecules. You could too. Let's just look at these. This is 1 sodium, 1 chlorine, 1 hydrogen, 1 fluorine, 2 hydrogens, 1 oxygen. We'll talk about these guys in just a little bit. Those are called polyatomic ions. If you take 1 sulfur and 4 oxygens, they bind together covalently and form an ion with a charge of -2. This ion then pairs with 2 potassiums, which are +1. But we'll do that one just a little bit later. All right, when we go to name these things, it's really, really simple. First word of the name is just going to be the cation. That's all you put down. The second word of the name is going to be derived from the anion. What you're going to do is look at the element, pick out the root, and then you're just going to add IDE. If you have more than one of anything, you don't use a multiplier, it's just the simple name. So let's see what this looks like. Here our cation is magnesium. The first word of the name would simply be magnesium. Separate word, space afterwards. Our second element here is bromine. The root for bromine is going to be brome. So we take the root and we simply add IDE. This is magnesium bromide. 2 words. We do not include the multiplier, so this is not magnesium dibromide. Now that makes naming them very, very simple. But if I tell you you have magnesium bromide and you were supposed to write a formula, you have to know magnesium is going to be +2, bromine is going to be -1, so we need 2 of them. So it makes it easy going forward, a little more difficult going back. Sodium is our cation. Chlorine is the anion, and its root is chlor. So we would simply do sodium chloride. This is potassium. The root for sulfur is sulf. And all we do is stick IDE on the end. Beryllium and bromine. Beryllium is in group 2, so it's a +2 ion. Beryllium is our first word. Again, we've already done bromine. We know this is going to be bromide. Simply add IDE. Once again, no multipliers. Any questions? All right, let's just do a couple really simple exercises here. Go ahead and write the formula for a compound made from magnesium and chlorine. First step, you have to find them on the periodic table, see what group they're in. Once we know what group they're in, we can simply assign the charge for the cation and the anion. Well, magnesium is right here in group 2. That means it's going to want to be a +2. Chlorine is here in group 7, so it's going to want to be a -1. All right, we have to balance our +2 charge with 2 negatives. So we need 2 chlorines for every magnesium, and we would simply write it MgCl2. The name of this would simply be magnesium chloride. Any questions? How about aluminum and oxygen? Find aluminum. Find oxygen. Well, aluminum lives here in group 3, doesn't it? So it's going to want to form a +3 cation. Oxygen lives here in group 6. It's going to want to gain 2 electrons and be a -2 anion. Aluminum is +3. Oxygen is -2. All right, so what we're working with here, aluminum +3, oxygen -2. Remember, the principle of charge balance says we have to come up with a neutral compound. So, here's what we have, aluminum and oxygen, right? There's actually a really simple little trick you can do to do this. Just go ahead and write your elements down. Now, the charge on the first one is going to be the subscript on your second one. The charge on the second one will be the subscript on the first one. So they simply cross over like that. If you think about it, we have 6 positives and we have 6 negatives. Nice simple little bit of symmetry there. Make it easy for you. Any questions? We would name this aluminum oxide. No multipliers. The root for oxygen is ox, and we just add IDE. One more, let's do beryllium and selenium. Step 1, we have to find them. Beryllium is this guy right here, isn't it? In group 2. Because it's in group 2, it's going to want to form a +2 cation. Selenium. Selenium is over here, just below sulfur. It's in group 6, just like oxygen was. And just like oxygen and sulfur, it's going to want to pick up 2 electrons and form a -2 anion. So we have a +2 and a -2. Now, we could do the same little symmetry crossover here, like this, but that would be wrong, wouldn't it? Because we always want the lowest whole number ratio, so the 2's don't work. We just write BeSe. Once again, this is what it looks like, and it's crystal, little tiny beryllium, big sulfurs, in a very nice array. We named it. The root here is selen. So this is beryllium selenide. All right, everyone have this? Go ahead and very quickly write down appropriate names for these guys. Our first one, our compound is made from calcium and bromine. First word is going to be calcium. Our root here is brome, so this is calcium bromide. Here we have aluminum and oxygen. Our first word is simply going to be aluminum. This is going to be oxide. Here we have lithium and sulfur. Our first word is simply lithium. Our second word is going to be sulfide. Calcium and oxygen. First word is simply calcium. Second word is simply oxide. And finally, nickel and chlorine. Now, if you look at the periodic table, nickel is here in the transition metals. Still a metal, but you can't do the thing about looking at the group number to get the charge. We would call this nickel chloride, but that wouldn't quite be right. You see these guys in the middle, all of these transition metals, they can actually form cations with different charges. +2, +4, +6, whatever. Therefore, we'll see in just a little bit. To properly name this, we would have to indicate what the charge is on our nickel. We know that chloride is going to be -1, right? So if this guy is neutral, nickel must be +2. We will do this by writing nickel 2 in Roman numerals immediately after the word nickel, space chloride. But again, we'll do that later. You only have to do this for transition metals. These guys in the middle. Any questions? Let's work backwards here. Here I have some names. Go ahead and write the formula for me. You see, now it would be nice if we had multipliers, wouldn't it? Because we would know exactly how many calciums, exactly how many nitrogens. Calcium, we look at our periodic table, it's in group 2. It will be a +2 ion. Nitrogen is over here in group 5. So it will be a -3 ion. So what we have here is +2 and -3. Again, we have to come out neutral. So you can do the crisscross, and when you do, nitrogen would be -3, so we need 3 calciums. Calcium is +2, we need 2 nitrogens. Total 6 positives and 6 negatives. On the exam, you will have a periodic table. Don't worry. Magnesium oxide. Magnesium is group 2, so it will be a +2 ion. Oxygen is group 6. It will be a -2 ion. So we simply need 1 magnesium, 1 oxygen, and that's what we have. Lithium is in group 1. It'll form a +1. Iodine is in group 7. It will form a -1. So once again, we just need 1 of each. Barium is in group 2, so it's a +2. Phosphorus is in group 5, so it's a -3. So again, we have +2, -3. Our -3 means we're going to need 3 bariums. Our +2 means we're going to need 2 phosphorus. Ba3P2. Yeah.
Now I'm kind of confused on like the chart. Like how do you know by each group?
Well, the first 4, so 1, 2, 3, and 4, we're going to do cations. +1, +2, +3, +4. Okay? For the anions, we start here in group 7. That needs 1 electron to get over to a noble gas, right? So that's going to be -1, -2, -3. So +1, 2, 3, 4, -1, 2, 3.
So how about that last row? Like, what happened?
These are the noble gases. Everybody's trying to be one of those.
Oh, okay.
Nobility, right? They have full valence shell, so they don't form ions, and they really don't form much in the way of compounds. That's why they're called inert. All right, the last one here, beryllium fluoride. We saw beryllium is in group 2, so it's a +2. Fluorine is in group 7, so it's a -1. We're going to need 2 fluorines for every beryllium. Now just practice these with your periodic table. Again, remember, groups 1, 2, 3, 4 are simply going to be cations with +1, 2, 3, sometimes +1. And then start at group 7 and work the other way, -1, -2, -3. All right, I promised you that we would talk about polyatomic ions. Polyatomic ions are neat. It's a group of atoms that are bonded together with covalent bonds. So all the atoms in this little lump are sharing electrons. Within this lump, we have an extra electron or 2 or 3 or whatever. that makes this lump of atoms charged. This is called a polyatomic ion. An example here, strontium sulfate. Strontium is a group 2 element, so it's +2. Sulfate is 1 sulfur and 4 oxygens. Again, all covalent with a charge of -2. In strontium sulfate, we have 1 strontium and 1 of these sulfates. Put them together in a crystal, looks like this. There's our strontiums, and the sulfates are all around. Once again, they're stuck together electrostatically, the pluses and the minuses. Now, problem with polyatomics is that there are a lot of them. Yes, there are. And yes, you do need to know these. Yes, you do. Now, on the first exam, I'll probably help you a little bit. But as we go through the course, you'll use most of these so many times that it'll become really simple. You'll know what they are. We're going to run through these guys one at a time. Just take a look at them. There's one general guideline that can help you within a family. This works for oxygen-containing polyatomics. Just like sulfate, we have oxygens in there. What you want to do is find the parent. Sulfate is the parent, okay? It's going to end in ATE. It'll have a certain number of oxygens. So remember the parent. If we have one more oxygen and add it to it, we're going to put a per in front. So we could call it persulfate. That means too many oxygens. If we have one less oxygen, we're going to change the ATE to ite. So it would be sulfite. And finally, if we have 2 less oxygens, we put a hypo in front of it, hyposulfite it would be. All of these, everything in the family, will still have the same charge. So if you kind of remember this trend, it'll help you deal with it. Within every family, try to remember what the parent compound is, and then these other things you can just add and subtract oxygens. Again, they all have the same charge. So let's just run through the list here. Nitrogen. If we have a nitrogen with 3 oxygens, that's our parent, and that's called nitrate. It has a -1 charge. We take 1 oxygen away, it's still -1, but now we call it nitrite. And this is what nitrate looks like here. The only positive polyatomic that we're going to deal with is this guy here. This is ammonium. Everyone's heard of ammonia. Well, if we simply put 1 more hydrogen, 1 proton on ammonia, we get this polyatomic, nicely tetrahedral, with a net positive charge. So ammonia goes to ammonium. Only positive one we have to deal with. We saw sulfur. Again, our parent is sulfate. -2. Take 1 oxygen off, we get sulfite. Now there's another thing that these things can do, and that is we can put a hydrogen on one of these oxygens. When we do that, we will simply change the name to stick hydrogen as a separate word in front. So this is hydrogen sulfate. When we put the hydrogen on, it takes one charge away. This would be sulfite. Therefore, this is hydrogen sulfite. This is what sulfite looks like. This is what sulfate looks like. Phosphorus, parent is PO4 3-. Take one oxygen away, we get phosphite. Add hydrogens. One hydrogen, charge goes down, hydrogen phosphate. Add two hydrogens, charge goes down, dihydrogen phosphate. Here I did phosphite because you can do the same thing. Dihydrogen phosphite. Carbonate. Carbonate is the parent, and it's a single parent, unfortunately. There is no carbonite. Now there was in Star Wars, wasn't there? But that's only in Star Wars. Is no carbonite. Put a hydrogen in front, hydrogen carbonate, also called bicarbonate. Sodium bicarbonate, you've all heard of that. It's really sodium hydrogen carbonate. Acetate we won't deal with too much. Cyanide is poison. This is oxalate. These guys follow the chlorines, just follow the rule perfectly. The parent here is going to be chlorate, ClO3, -1. Add an oxygen, we get perchlorate, too many oxygens. Take one away, we get chlorite. Take two away, we get hypochlorite. Boron, we're going to do borate. No children. And when we do acids and bases, hydronium and hydroxide are actually polyatomics as well. These guys you probably don't need to know for the exam. Any questions? All right, well, keep your little list handy, okay? Because we're going to name some of these, and it's okay to go back and look them up. But before we do, I said that the polyatomic ions were covalent compounds. Let's demonstrate that by doing a Lewis structure for chlorate. Now, when we do Lewis structures, remember, we need to find the atoms. We need to figure out how many valence electrons they have. And then we need to try to arrange them so that everybody has 8. Okay? That's the simple procedure here. Step 1, chlorine is here in group 7. So it's going to have 7 valence electrons, right? So we'll put the chlorine in the middle with 7 little dots around it. Oxygen is in group 6, so it will have 6 valence electrons. Put the 3 oxygens around the chlorine, give them all 6 dots. Here's our chlorine in the middle. 1, 2, 3, 4, 5, 6, 7 electrons. Here's our oxygen. 1 pair, 2 pair, 2 single. Single, 1 pair, 2 pair, 2 single. All right. We need to form bonds, don't we? Clearly, we can't form a bond here with 3 electrons. So we're going to have to move one of these guys up there, one of these guys up there. That's good. But remember, this is an anion. So we have an extra electron in here, don't we? The extra electron is going to go here on the chlorine. When we do this, We have an extra electron in this group of atoms, so the whole group now has a negative charge. Now all you have to do is make bonds. Here's 2 electrons we can share, 2 we can share, 2 we can share, and we're good. Oxygen has 8, all of them do. The chlorine in the middle also has 8. We draw this using bonds. It would look like this. Remember, the whole unit here has the negative charge. All right, let's see if we can name some of these guys. These are the common ones that you will see often on exams and quizzes.
For the exam, would our questions be multiple choice primarily, or
I'm sorry, but
for the exam, would the questions be
oh, it's so exciting. Look at the exam. The sample exam will be exactly like the real exam. Just all the answers are different. But I do that on purpose so that you see the sample exam, you work it, you feel really good for yourself. Okay, hey, I did this, that sort of thing. And then you see the real exam, and it looks exactly the same. Physically, it looks, all the questions are different, but it looks exactly the same. And it makes you feel comfortable because you've done that once. So you'll see what they look like. Our first, the cation is calcium. So we will write the word calcium. We remember that the carbon polyatomic is carbonate. There's no carbonite. So this is simply calcium carbonate. Calcium is +2, carbonate is -2. Our next guy here, this is our cationic polyatomic. Based on ammonia, this is ammonium. So the first word of the name would be ammonium. We have a chlorine at the end. This is simply ammonium chloride. Here we have sodium, that's our first word. And the parent in the sulfur group is sulfate. Sulfate has a -2 charge. That's why we need 2 sodiums to balance it. Our first word here is lithium. This is a sulfur derivative, but it has 1 less oxygen than sulfate, doesn't it? It'll have the same charge, -2, but we will call it sulfite. And finally, phosphate has a -3 charge. We put 1 hydrogen on, that makes it a -2 charge. We need 2 potassiums at +1 each to balance it. Our name, let's say we have potassium, 1 hydrogen, and a phosphate. Now that's not so hard, is it? Let's do it backwards. Now you can look up what permanganate is. I would not give you something like permanganate on the exam. Permanganate is MnO4, and it's a -1. Potassium, of course, is K, group 1 plus 1. This is simply KMnO4. Potassium permanganate is used in commerce a lot. It is very, very bright purple. It's what's called an oxidizing agent. It's used to purify water, kill bacteria, all sorts of stuff, treat sewage, etc. It's very, very common. Barium. Barium is group 2, so it's a +2 cation. Sulfite. We know that the parent there is sulfate, SO4, and it has a -2 charge. Sulfite would be SO3, also with a -2 charge. So this is simply barium and SO3. Aluminum chlorate. Chlorate is the parent. It has a -1 charge. Now aluminum is in group 3, so it has a +3 charge. So for every aluminum, we have to have 3 chlorates, don't we, to balance it out. These guys are -1. This is +3, so we need 3 of these. How do you show that? Just put our aluminum, and then we have our chlorate, and we put it in parentheses, and another subscript to indicate we have 3 chlorates. Silver nitrate. Oh, I threw a ringer in here because silver is a transition metal down here, isn't it? How in the world do we know what charge it is? Simple. It's always +1. Always +1. Just don't worry about it. Whenever you see a silver, it's going to be +1. Nitrate. Nitrate is the parent of the nitrogen group. It has a -1 charge, and it's NO3. And finally, barium cyanide. Cyanide is poisonous. Again, probably wouldn't put cyanide on your exam, but it might show up on a tutorial. Barium is +2. Cyanide is -1, so we need 2 of them. 2 cyanides to balance our +2 barium. We're going to do it the same way we did up here. We're going to put our cyanide, which is CN, in parentheses and indicate that we need 2 of them. Make sure you put the parenthesis, okay? Otherwise it would read CN2, saying there were 2 nitrogens for every carbon. That's wrong. All right, this is simple. Go ahead and just jot down the names for these guys. Well, Pb is lead, in case you don't remember. And of course, Fe is iron. Our first one here, we have 1 lead, 1 oxygen. Our first name is just going to be lead, right? And our second word is going to be oxide. Now our second one here, our first word is going to be lead. We don't use multipliers, so this is lead oxide. Iron and oxygen. Iron oxide. Iron and oxygen. Iron oxide. Obviously, there's something wrong here. That's because lead and iron are transition metals. So they're in the middle. They're not in our main groups. And they can have different charges, just like we saw for nickel. So what we're going to have to do is put down the charge for all of these. This is called the oxidation number. Now the oxidation number is nothing more than the charge on these ions. If you look at the periodic table and you find an element, the oxidation number is actually defined as how many electrons you put on or taken off that given element. So it's just like the charge. You put electrons on, make it a negative charge, take them off, make it positive. We're dealing here with the transition metals, and these are all going to be positives. If we had magnesium bromide, magnesium we know is in group 2, so its charge is +2. We could say the oxidation number of magnesium is going to be +2, and the oxidation number of bromine is going to be -1. For lithium phosphide, lithium is +1. Phosphorus is -3. We could say this in terms of oxidation numbers simply by saying oxidation number of lithium is +1, oxidation number of phosphorus is -3. So it's the same sort of concept that you already know. It's just got a different name to it. Any questions? There are actually rules for assigning oxidation numbers. We really aren't going to mess with too many rules. I don't like rules. Most of you don't either, I'm sure. This is what this set of rules actually looks like. If you're dealing with a pure element, it's 0. Group 1 is always 1. Group 2 is always 2. Fluorine is always -1. This one, forget. But the ones that you really want to remember are going to be these guys. With few exceptions, oxygen is going to be -2. Okay? You can pretty much take that one to the bank for this course. Other thing, anytime it's a halogen, that's group 7, it'll be -1. Those are the only 2 rules you really need to remember. All right, that makes it simple. So let's assign oxidation numbers here. We know both of these are lead oxide, aren't they? Oxygen, we just said, is going to be -2. If this is a neutral compound, what's the charge on the lead? Has to be +2. Here we have 2 oxygens, and they're going to want to be -2 each. So this is 4 negatives, isn't it? For this to be a neutral compound, the lead must be +4. Let's go back to our iron. Remember, SO4 is sulfate, right? And we all remember sulfate is -2. So, if sulfate is -2, the charge on the iron must be +2. And finally, here you have to do some math. Each oxygen is going to be -2, isn't it? So we have a total of 6 negatives. We have 2 irons, and they have to balance out 6 negatives. Therefore, the iron must be +3. You can do your little crisscross in reverse. We have 3 oxygens, so iron must be +3. We have 2 irons, so the oxygen must be -2. Same sort of thing. 6 positives, 6 negatives. Any questions? Well, once we figure out what the oxidation number is, how do we put this in our name? Well, just like we saw with nickel. We're going to write it using Roman numerals. Going to write it right next to the cation and put it in parentheses. This is going to be lead. We have 2 oxygens at -2 each, so this must be a +4. We would write lead 4 oxide. 1 oxygen at -2, so the lead here must be +2. And we would write lead 2 oxide. Carbonate, the parent of the carbon family, is -2. If carbonate is -2, the iron must be +2. So we write iron 2 carbonate. Bromine is group 7. It is a -1 ion. We have 3 of them. In order to be neutral, the iron must be +3. So this is iron 3 bromide. Now, I would not be doing a good job if I didn't write a tutorial for this, would I? Here we go, binary ionic compounds, formulas to names. This again will earn you 5 points if you do it twice. All you have to do, click new formula, something will show up. And then you very carefully type your name here. We have a barium and we have iodine. The root here is going to be io and ioda, and we're going to add I to it, so it's iodide. Barium iodide. And this will tell you if you screwed up the first name or the second. Go ahead and do this one. Now, this is a little trickier because copper is a transition metal, isn't it? So here you have to actually enter the Roman numeral in parentheses right after the copper. Iodine. Group 7, it'll be -1. If this is neutral, copper must be +1. So we simply type in copper 1 iodide. Do one more. ClO. Now this is the chlorine family, right? Chlorate was the parent, ClO3. This has 2 oxygens missing. What do we call that? It'll be a chlorite with the hypo in front. Hypochlorite. It is -1. We have 3 of them, so the iron must be +3. This would be iron 3 hypochlorite. Ever heard of sodium hypochlorite? Ever heard of bleach? Bleach is sodium hypochlorite. Any questions? All right, we're halfway through naming. Now let's look at molecular compounds. Here, we're going to do the same sort of thing. We're going to name the first element. We're going to add "ide," just like we did before, except now we're going to use multipliers. The way you count in chemistry is mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. That's how you count in chemistry. Here we have 1 carbon and 4 chlorines. Our first word is simply our first element. We do not use mono if we only have 1 first element. So we don't use mono, we simply say carbon. Now our next word is going to need a multiplier. We have chlorine. We know that that's going to be chloride, right? And how do you say 4? 4 is tetra. So this is carbon tetrachloride. Carbon tetrachloride is a wonderful solvent. Back in the old days, if you went to an auto shop, they would have a whole barrel of the stuff sitting there open. And if you had a dirty carburetor, they'd take it, slosh it around in there, wash all the gunk out, worked really great. Carbon tetrachloride is now considered a very severe carcinogen, so you don't do that anymore. But it's a great solvent. 1 sulfur, 2 oxygens. We don't use mono, but we only have 1 first element. So our first word is going to be what? Just sulfur. Here we have 2 oxygens. It's going to be an oxide, isn't it? How do you say 2? Well, the prefix is di. So this is sulfur dioxide. Now we have 2 of our first element. Now you need a multiplier. We're still going to call it nitrogen. It's just we have to tell the world that there are 2 of them. So this simply is going to be dinitrogen. Now, we only have one of our second element, but the second element always gets a multiplier. This is oxygen, it'll be an oxide. So we're going to call it dinitrogen monoxide. Now you'll note, if you actually count, that we're missing an O. If we stuck mono there, there would be two O's in a row, and that just looks ugly. So you just don't do that. Nitrogen monoxide. Once again, we have two nitrogens here. So we know our first word is going to be dinitrogen. We have 5 oxygens. How do we say 5? Well, that's penta, isn't it? So we would write this as pent oxide. Once again, we're dropping out a letter if we have too many vowels, because it just doesn't work. So pentoxide is what you would do. Now, if this was an exam or something and you wrote that, I would not be bothered at all. Okay? So, but this is the proper way. All right, let's go ahead and just quickly jot down this list. We have 1 carbon and 2 oxygens. Our first word is going to be carbon. We say 2 with the prefix di. So this is simply carbon dioxide. We have 2 hydrogens and 1 sulfur. We have to say a multiplier for our first atom. So it will be dihydrogen. We only have 1 sulfur, so we have to say this is monosulfide. Now H2S is commonly called hydrogen sulfide. It is the smell of bad well water. It's actually a fairly toxic compound. In high enough concentrations, in well water, it's okay. 1 silicon and 4 hydrogens. No multiplier for the silicon, so we just write silicon. We have 4 hydrogens, that's going to be hydride, and our multiplier is simply tetra. 1 sulfur, 3 oxygens. First word is sulfur. For 3, we do tri, don't we? So this is sulfur trioxide. One nitrogen, 3 chlorines. This first word is simply nitrogen. Again, our multiplier is trichloride. One more set, a little more interesting. We have phosphorus, and we have 4 of them. So this is going to be tetraphosphorus. We have 6 sulfurs. 6 is a hex. So this is going to be tetraphosphorus hexasulfide. 2 iodine, so it's going to be diiodine. And we have 7 oxygen. Remember what 7 was? Hepta. So this is going to be a hepta oxide. Drop the extra A out. Diiodine hept oxide. One oxygen, no multiplier. 2 fluorines. It'll be a difluoride. Now this next one is a trick one. 1 carbon, so we'll call that carbon. 4 hydrogens, that's a tetrahydride, right? This is methane, natural gas. Nobody in the right mind would ever call it carbon tetrahydride. This is methane. And finally, 4 sulfurs. That's a tetra. Tetrasulfur dinitride. So these were a little more fun. Now, the nice thing about molecular compounds is going backwards. If I give you a name, all in the world you have to do is read multipliers. Go ahead, quickly jot down the formula for these guys. Well, we have 1 nitrogen, and tri is 3 iodides. We have 2 phosphorus, pent is 5 oxygens. 1 sulfur, 3 chlorines. 1 nitrogen, 1 oxygen. No. 1 hydrogen, 1 chlorine. Isn't it so nice and simple in reverse? Any question? All right, let's do a reality check. We said that these are covalent compounds, right? We said that when we make a covalent compound, we share electrons. Well, sort of. Consider chlorine and sodium chloride. Here we have a covalent bond. We have the same atoms. Because of that, the sharing here is perfect. They share just like siblings, okay? I'll make it better, but they share. Here's the other limit, sodium chloride. Chlorine took the electron from sodium, boom, just took it away. No sharing there at all. So those are the 2 limits of bonding. In reality, when you form a covalent bond between different elements, the sharing is going to be very imperfect. This is just a simple example here. This is hydrogen, H2. They're both the same. we can calculate where the electrons are around the molecule, okay? And we can show where they are using what's known as an electrostatic potential map. The electrostatic potential map will tell us basically where the electrons are, okay? So for hydrogen, we begin our calculation, and the calculation basically says that the electrons live in this kind of oblong sphere surrounding the two hydrogen atoms. Now, when we convert this to an electrostatic potential map, we color it. The color here is essentially uniform because we have nice, even sharing. This molecule is hydrogen fluoride. We do the same operation that we just did, the same calculation, and what we get for the electrostatic potential map is this. It's a gorgeous little Easter egg. Now when we color, the blue color is associated with an electron deficiency. Red color, we have an excess of electrons. What this tells us is that this covalent bond isn't really being shared very nicely at all, but the electrons in this are almost always here and leaving the hydrogen positive. This is what's known as a polar covalent bond. And we show polar covalent bonds using what's known as a dipole. Just an arrow, you cross one end of the arrow to indicate the positive end. You don't have to color it. Well, it'd be nice if you could, but just an arrow, positive at one end. We say that hydrogen fluoride has a dipole moment. Now, how can they get away with this? What causes this? It's a phenomenon known as electronegativity. It's a simple physical property. And all it does is describe how strongly an element attracts electrons towards itself. In the periodic table, there's basically a ramp. Down here, we have the lowest electronegativities. Up here, fluorine is the highest. It kind of goes across and up, but essentially it ramps up from here to here. The lesson here is that if you have a covalent bond between atoms that have different electronegativities, it's going to be polar. Now that's going to become important to us when we talk about acids, because polar covalent bonds can break, and that makes an acid. All right, let's just go back to our nomenclature and just do this one more time quickly. Write me a compound with a sodium and a sulfate, a barium and a chromate, aluminum and a carbonate, etc. You may look at your little sheet if you don't remember where's who. Something like sodium and sulfate is the degree of difficulty that you would easily see on this first exam. Sulfate, we know, is a -2 polyatomic ion. We look it up and it's SO4, -2. Sodium, group 1 is +1. We simply have sodium and sulfate, putting them together in a 2SO4. Chromate is one that we're not going to have on the exam. Barium we know is +2. Chromate is CrO4 with a -2. Barium is a +2. We essentially need one of each. Aluminum we know is a +3. Carbonate, CO3, and it's -2. We could do our little crisscross here, couldn't we? We're going to need 2 aluminums and 3 carbonates. Go ahead and make sure you can write the formula properly using parentheses. This is simply 2 aluminums and 3 carbonates. Magnesium we know is going to be +2, group 2 metal. Phosphate, PO4, -3. But if we put 2 hydrogens on, that changes the -3 down to a -1. All right, so to make this neutral, we need 1 magnesium and 2 dihydrogen phosphates. And finally, beryllium hydroxide. Beryllium we know is a group 2 metal, so it's a +2. Hydroxide, that's our polyatomic, OH, and it's -1. That's what makes things basic. We're going to need 2 hydroxides for every beryllium to make this neutral. Make sure you show the OH in parentheses. Otherwise it would read 1 oxygen and 2 hydrogens. Any questions? All right, this is a question off an old exam that everybody missed. It's so incredibly simple. How many protons in the anion sulfide? Here's our periodic table. Here's sulfur. If we were to write the atomic symbol for sulfur, what would we do? We would write the number, the atomic number, as our subscript, right? This one doesn't have mass, but over here, if you look at sulfur, it would be 32 for a mass number. And we said that this is a dianion. So that's what our atomic symbol would look like. Now, how many protons does it have? That's the atomic number, isn't it? Doesn't matter if it's an anion. So the question really should be, how many protons are there in sulfur? It's just its atomic number. I'm going to skip this next question because we did it already. This is off old exam. Quickly, name these guys. No. No, you can't just name it no. We have a nitrogen here, don't we? No multiplier. And we have an oxygen, one of them. Nitrogen monoxide. One silicon, so it's just silicon is our first word. 4 is tetra. We have 2 phosphorus, so we have to use di, don't we? Di, phosphorus, pentoxide. 1 carbon, no multiplier, 2 oxygens, dioxide. So this is the level of nomenclature you can look for on the exam. You can also look for this. Go ahead and take these guys and name them. Maybe not cyanide, okay? I told you no cyanide. CS is cesium. It's group 1. We have SO4, that's 2 minus, that's sulfate. So this is simply cesium sulfate. Mg is magnesium. As I said, Cn was cyanide, no multiplier. NO3 is nitrate. We have 1 potassium, no multiplier, obviously, potassium nitrate. The parent here is PO4, that's phosphate. We're missing 1 oxygen, so this is phosphite. And this is calcium phosphite. Na is sodium, SO3 would be sulfite, and we have a hydrogen. 3 words, sodium, hydrogen, sulfite. All right. When we talked about molecular compounds, I said that they differed from ionic, both by the way they bonded. But the really neat thing about molecular compounds is that they actually have a shape. They have a unique shape. All covalent compounds do. What we're going to do is just look very quickly at how we know what these shapes are. This is some examples. This is 1 carbon, 4 hydrogens. This is methane, CH4. Methane is tetrahedral. Now, they teach lots of shapes in kindergarten, but for some reason they never teach tetrahedral. I don't know why. Tetrahedral is very important. The carbon here is in the middle of all of these guys. They all have the same bond angles. They all have the same distance. That's a tetrahedron. This is ammonia, NH3. NH3 actually looks like this. It's kind of puckered, bit down. We have 3 bonds going there and our nitrogen in the middle. Phosphorus pentafluoride looks like this. Phosphorus in the middle, 3 fluorines around the middle, and 2 axiofluorines. So how in the world do you know? Turns out it's very, very simple. It's called the valence shell electron pair repulsion theory. And the basic thing is that electron pairs, like in bonds or even unshared, they're all negative, and they want to be as far apart from each other as they can. So a molecule gets its shape because these electron pairs want to be as far apart as possible. If we start off with 2 electron pairs, the way to get them as far apart as possible is to make them linear like this. 1 here, 1 over here. If we add another one,
According to VSEPR theory, the valence pairs surrounding an atom move to positions that minimize their repulsions.
that's tetrahedral. So the first one that came in gave us 3 trigonal. And here we are with our 5. Well, we can even go more. Add a 6th, and we get what's known as octahedral. We're not going to do that. If we have 2 things, again, the electron pairs want to be as far apart as possible. Looks like this, and it's linear geometry. If we have 3 things, we're going to form a triangle with these guys, and we'll call it trigonal, simple triangle. If we have 4 things, we can do our tetrahedron. And once again, note that the central atom here is in the middle of this shape, and all these are the same distance and the same bond angles. Here's another way to look at it: linear, trigonal, and here's our tetrahedron with this hiding in the middle. Let's go ahead and figure out what ammonia would look like. Remember we saw ammonia as kind of this funny looking thing, right? Well, it's in H3. If we draw the Lewis structure, nitrogen is group 5, so it has 5 electrons, right? Hydrogen group 1, it has 1 electron. We would draw something like this. Now what you do is you look and you say to yourself, how many electron pairs are around this nitrogen? Well, it has 3 that are involved in bonds, right? And it's got this pair that are just sitting here. So all of these are going to want to be as far apart as possible. The way to do that is to take our 4 groups and arrange them in a tetrahedron. If you just look at the atoms, this looks like it's a little tiny pyramid. But if you count the electron pair here, this is tetrahedral. The number of things you have is actually called a steric number. You'll do that in general chemistry. This would be a trigonal pyramidal, again with the 4th thing sticking up here. We can have, well, this is what we just did, trigonal pyramidal, Again, it's a tetrahedron, but we just don't see the electron pair that are sticking up. Now, water is something that's going to be very important to us when we do acids and bases. Let's do the same exercise here with water. Water, oxygen is group 6, 6 electrons. Each hydrogen has 1. Our Lewis structure would look like this. Now you ask yourself the same question. How many electrons do we have around our oxygen? We have these two that are in bonds, and we have 2 extra pairs. The way to make these get as far apart as they can, steric number is 4 again, is to make this into a tetrahedral. We don't see these guys, they're just electrons. And if you look at the atoms in water, they look like they are bent. Goes up and down, but it's actually the corners and the middle of our tetrahedron. There are 3 varieties of tetrahedral geometry depending upon your electron pairs. If we have 4 things, we can have a full tetrahedron. 3 things is pyramidal, and 2 things is bent. We will see that the fact that water is bent is one of the things that makes water such a powerful solvent, something that we literally cannot live without. And it's simply because of the geometry. All right, I think this pretty much kills the chapter. We had one more tutorial today, okay? That was the Ionic, binary ionic compounds. Again, make sure to add that to your tutorial list. There's also